So when we're talking about static and kinetic friction, we have to obviously know that friction is a resistive force. So let's say we have a block over here and our motion is going to the right. Well, friction is going to oppose that motion and move to the left. So the whole job of friction is to oppose motion. That's literally what friction does. And we can break it down into two types of friction. We have our static friction and we have, let me change my color over here, we have kinetic friction. Kinetic friction. All right. So what's the difference between static friction and kinetic friction? Well, a great example I like to think of is thinking of pushing a couch. So let's just say this is a couch over here. So let's say that we wanted to push this couch just for whatever reason. Maybe we're moving out or something like that. And our applied force is going to move to the right. We're moving to the right. So I'm going to put F and this is our applied force. Well, static friction is going to be the friction that prevents this couch from moving. So static friction is going to be applied when we are at rest. So this is the resistive force that prevents motion. So when you try to push a big couch, obviously you're not going to be able to push it if you put like barely any force. But when you put enough force, let's say you put all of your effort to pushing this couch, then you finally move this couch, that's when we move into kinetic friction. And kinetic friction is when we have friction at motion. So this is the friction at motion. So let's say that we are moving this couch over here. We're moving it. Our kinetic friction is going to be obviously opposing this motion. So this kinetic friction, it could be smaller than this applied force if we're accelerating, like if we're actually, pushing this thing. But more than likely, when we push a couch, we're most likely going to push it at a constant speed. But nevertheless, kinetic friction is going to be the friction applied when we have motion, while static friction is going to be applied when we're at rest. The formulas for each of these guys are our static force is going to equal the coefficient of static friction times our normal force over here, and same guy over here but with kinetic, so just with K. So it's going to be kinetic force equals our coefficient of kinetic friction times our normal force. Now, another couple things to know is that static, like we talked about with static friction, there is going to be a maximum. So there's going to be a maximum static force, or static force, in which we will overcome that, and then we move to kinetic force. So static friction has a maximum, while kinetic friction over here, this is going to stay constant. So no matter how much we push this couch over here, our kinetic friction will stay constant. And one last thing to note with our static and kinetic friction is that our coefficient of static friction will be greater than the coefficient of kinetic friction, something like this. So what we'll see, and let's say we were pushing this couch. So I'm going to actually bring out a graph over here just to visualize the forces that are going on. So let me create this guy over here. And let's say on the bottom, this is the force applied. So this is the applied force that we put on the couch. And let's say, let me change my color to, let's go red. And then this is going to be our frictional force. So I'll just put frictional force over here. So this is our frictional force. What happens is when we're pushing the couch, we're pushing it, applying more force, and our frictional force will also increase, but we're not moving the couch. But the moment we finally move that couch, that's when we turn into kinetic force over here. And with that kinetic friction being applied, it will stay constant, and it is less than the static friction that we had, that frictional static friction we had. So just to sort of put this in layman's terms, over here, this is where we meet that max, that F max that we were talking about, the maximum amount of frictional force in which we turn into kinetic friction. So over here, we're moving the couch won't budge until all the way over here, where the couch finally moves, we get maybe a little bit of a slip or something, and that's when we move to kinetic friction. So knowing that, this is where we move on to ramps. And this is where most questions, especially the MCAT, really try to test your knowledge on static and kinetic friction. So over here, we're usually going to have some sort of structure like this, like a ramp over here. They might even give you the degrees over here, that theta over here. And first off, we need to draw our free body diagrams. We need to draw those forces. So over here, this force over here is our normal force. And remember, normal force will always be perpendicular to the surface of this object. So the surface over here is this ramp, so perpendicular to that is our normal force. Now you might be used to seeing just objects on the ground and then you just point up, then that's our normal force. But with our ramps and pretty much every other example, our normal force must be perpendicular to the surface. Now that's a little bit different though from our weight, and our weight will always be pointed down. That weight or gravitational force, which is mg, which will always be pointed down because gravity will always be pointed down. Now let's start doing some labeling, and this is where we get into some forces that will help us find our static and kinetic frictional forces. So over here, this force over here is going to be, let me label that, this force over here is going to be our force that is perpendicular to the surface, and this is going to be mg cosine theta. Now over here, the force that is parallel to the surface, so this is pretty much the force that's allowing our block to flow down, assuming that we are in motion. This is the force parallel, and this is going to be known as, or this is going to be shown as mg sine theta. All right, so now that we know that, we can bring up our frictional and kinetic forces. So with our ramp, we can make the assumption that our normal force equals mg cosine theta. Both of these forces are going to be the same in magnitude, so we're going to have mg cosine theta as our normal force. This comes in handy because if we remember from our equation, our static force equals our coefficient times normal force. We can substitute normal force over here, and that is when we get this equation over here, times mg, oh, that does not look like an mg cosine theta. And that is how we get our frictional static force. And if we want to do the same for our kinetic force, I mean, pretty much same thing, but just substitute k. So it's just going to be mg cosine theta, and this is our kinetic, and this is our static. So let's dive into some conceptual physics real quick, and let's say that I increased the angle of inclination over here. So let's just say we knew our kinetic friction, and let's say I increase this angle over here. What would happen to the kinetic force? Will it increase or decrease? So just to kind of illustrate this, let's say that this is our normal theta over here, and our increased theta would be something like this over here, and we still have that block. So would our frictional, our kinetic friction, would that increase or decrease? Well, if you said decrease, then you would be correct, because over here, our normal force, force N, this actually decreases. So our normal force decreases when we increase the angle of inclination. And by doing so, because we know that our kinetic force is dependent on our normal force, mg cosine theta, we know that our frictional force will actually decrease. So one thing you'll notice is that when you, let's just say you had a ramp and you put like a block on it, for example. If you have a lower angle, then, I mean, that block won't be able to move as much. But when you make that angle steeper and steeper, that block is able to move at a faster rate. All right, so now let's dive into our practice problem. And it states that we have a 5 kilogram block that rests on a 30-degree inclined plane. Question 1 asks, will the block slide on its own? And if it does, what is its acceleration? So let's start off by finding our weight, or we obviously know that it's going to be mg. So this is going to be mass times gravity, and our mass is 5 kilograms, our gravity is 9.8 meters per second squared, and this is going to get us 49 newtons. All right, so we know that. We can also do our free body diagram as well. So this is our normal force over here, then this is going to be our perpendicular force over here, perpendicular to the surface. Then we're going to have our parallel, might have to make that a little bit more straight. Parallel force over here, and we have our mg. So we know our mg is 49 newtons. Now let's try to find our parallel force. Now our parallel force, which is the force that, because we're wanting to know if the block slides on its own. So this is the force that would be responsible if that block would slide on its own. So this would be mg sine theta. Now we know that we have 49 as our mg and sine of 30. So if you guys remember, past trigonometry where we had to remember 30, 60, 90, those angles. So 30 would be, let's say 30 is over here, and this would be 2, and this would be square root of 3. So sine of this is opposite over adjacent, so this is going to be times 0.5. And when we do that math, we are going to get 24.5 newtons as our parallel force. Now, if we have 24.5 newtons, now let's try to find our perpendicular force over here. So our perpendicular force is going to be mg cosine theta, which is 49, and this is going to be square root 3 over 2, which that will be about 0.866. And if we do that multiplication over here, we're going to get 42.4 newtons. Okay, so we found our parallel force, we found our perpendicular force. Now let's try to find our maximum static friction. So we know that our maximum static friction, F, and then we'll do max S, this is going to equal our coefficient times our normal force. So we know that our normal force is 42.4. Now that we know that, because what we had to do is find our gravitational force over here, this weight over here. Finding that, we needed to find our parallel force, because this is what we're going to compare to see if our block is actually moving, to see if this force is greater than the frictional force. And we need to find our normal force, which is 42.4. So this is going to be, this is our static, so this point 0.3 times 42.4 newtons. And we're going to get 16.96 newtons. All right, so this is our maximum static friction. So if we get above 16.96, then our block is indeed moving on its own. And as you can see, 24.5 newtons, which is the force that's allowing this block to move, is greater than 16.96 newtons. So indeed, our block is sliding on its own. So that's how we answer question 1. Now question 2, if it does, what is its acceleration? Well, since now we're actually sliding, we can forget about our static friction and we talk about kinetic friction. So when we do that, we actually need to find our kinetic friction. So kinetic friction, or let me actually do with our big F, kinetic friction is going to equal coefficient of kinetic friction times normal force. So we know that is going to be 0.4 times 42.4. And when we do that math, we're going to get 12.72 newtons for our kinetic force. Now let's try to find our net force going down the ramp. So this is actually going to be our parallel force minus our kinetic force, because these are the only two forces that are now acting upon this block to cause that acceleration. So we're going to have Fk over here. So now this is just going to be our force net is going to equal our parallel force minus our kinetic, and this is going to be 24.5 newtons minus 12.72 newtons, and by doing that, we're going to get 11.78 newtons. So 11.78 newtons is our net force, and we know that force equals mass times acceleration. So if we just move the mass over, then we're just going to get acceleration equals force over mass, and our acceleration is going to be 11.78 newtons over, and our block was 5 kilograms, and this is going to end up being 2.36 meters per second squared. So let me move this guy over here to make it a little bit more pronounced. So This is our final acceleration, 2.36 meters per second squared.